All right, we're gonna get to our buffers and then our titrations, and we will continue titrations for a while, a few classes. And there is no class on Wednesday, I just found out. So somebody said, what are we doing since people were supposed to make stuff up on Wednesday? If you were supposed to make something up on Wednesday, I think I'm going to still be here. So just send me an email and you can probably still make up. Some people are going to make up a lab, I think. All right. So the problem here is we have 0.1 molar acetic acid, 0.2 molar sodium acetate. We left off on this one last week. So I'm going to run through this one again. And it asks for the pH. And so you have your HA and your A minus. There are three reactions that you need to know: the Ka reaction, the Kb reaction, and the Kw reaction. There are only three reactions you need to know, and they will answer everything. All right, if you look at how they do the homework, they may switch it around and do all kinds of different stuff, but if you stick with those three, you can get every answer, and this is what I'm going to stick with. When you're given HA and A minus, you can write either the Ka or the Kb. It doesn't make any difference. You would get the same answer. Since they give us the Ka, I'm going to write the Ka reaction. If they would have given us the Kb, well, then I would have written the Kb. But if I want to stick with the Ka reaction and you have both, and you know that Ka times Kb is equal to Kw, and Kw is a constant, 1 times 10 to the minus 14. So if you prefer to always work with the HA, great. You can just convert your Kb into Ka and do it that way. All right, so, but when you have an HA and an A minus, you can use either one. You got your H plus, you got your A minus. We have our HA, which is 0.1 molar. You got your A minus, which is 0.2 molar. And you have 0 of the H plus. Nothing was stated about H plus. All right, so the rule of Ca over Ka is greater than 1,000. That is true if you just have one thing, or if it's the K, or if you have a base, then it's the concentration of your base over Kb. All right, so if we just have an acid or we just have a base, we use that equation. If it's greater than 1,000, we don't have to check our X. I'm going to make it easier than that. When you have both the HA and the A minus, you have one reactant and one product that are not 0, you never have to check your X value. Always use your X1 value. It does not need to be checked. Since we have a 0.1, we have a 0.2, we know we can't have a 0. It's going to go to the right. So we have minus X, we have plus X, we have plus X. So we have 0.10 minus X, we have 0.20 plus X. And again, since we have concentrations on both sides, we don't have to check. If we did check, it would still say don't bother checking the X value. But you don't even have to do the Ca over the Ka because you have a reactant that's not 0 and a product that's not 0. The plus and minus X can always be neglected and does not have to be checked. All right, and so we have our Ka. It's 1.7 times 10 to the minus 5, and that's equal to the H plus concentration, which is X, the concentration of A minus, which is 0.2 plus X, but I told you that since we have a reactant and a product, that X value is very small, and it will not change the 0.20, so we are neglecting these, all right, because we know it's going to be small. All Ka values are small. All Kb values are small. When you have both a reactant and a product, that means even less is going to go to the right because of Le Chatelier's principle. You added a product, shifts it to the left, which means less coming to the right, which means X is even smaller than usual. All right, if you have a reactant and a product that are both not 0, you do not have to check your X value. Over 0.10 minus X, again, that is going to be neglected. All right, so you multiply both sides by 0.1, divide both sides by 0.2, and you get a 8.5 times 10 to the minus 6. I think that's right. Yeah. All right, and so there is your X value. All right, and now here's where you always have to look. If you assume in this one, you get it right, but if you want to be right 50% of the time, well, then X is H plus about 50% of the time. But if you go through all the work and you have your X, you have it right, check to make sure what X is. X is the H plus concentration. All right, half the time it's going to be H plus. And then less than half of the time it's going to be OH minus, and the other adds up to 100%. It's either going to be A minus or HA for your X value. All right, so now we know that this is H plus. So now we're going to take the pH. So pH is equal to the negative log of this concentration, 8.5 times 10 to the minus 6. And the pH of that is 5.07. Always give 2 decimals for pH and pOH. And always give 2 sig figs for your concentrations. And sig figs should not be an issue with losing points. All right, so we're going to see that this is actually a buffer. We're going to go through the definition of a buffer. But the key definition for a buffer is to identify if you have one or not. You have to have a concentration of your weak acid and a concentration of your weak base. H plus, OH minus must be 0. And you must have a concentration of HA and a concentration of A minus. Then you'll have a buffer. And buffers will stabilize a pH. So this is a buffer. We're going to go through, well, they go through that whole thing. They do it different than I do. Fine. All right, so buffers. So a buffer solution is characterized by the ability to resist changes in pH. All right, so I just said that we had a buffer and our pH was about 5. How to pick the correct acid-base system to make a buffer. If you want a pH to be 5, all right, you have to find a Ka value of the acid to be 1.0 times 10 to the minus 5, or something very close to that. Because if you take the negative log of that, so your pKa is equal to the negative log of your Ka, and so if that is equal to 5, all right, that is going to buffer, if you have both the HA and the A minus. If your pKa is 5, that means it's going to buffer it right at a pH of 5. If you wanted, and so our number for the last problem was 1.7. 1.7 times 10 to the minus 5. And if you take the negative log of that, it would round to 5, but it is less than 5, but it's very close to 5. So the negative log of 1.7, and fourth, you got a 4.77 as your pKa. All right, so this one, the previous had a Ka value of 1.7 times 10 to the minus 5, which gives you a pKa value of 4.77. I think. Let's see. 4.77, yes. All right, so that is a 4.77. All right, so that would be an excellent acid to pick to make a buffer out of, because that would buffer something at 4.77, which is pretty close to 5. And so we see that in the last one we had more base than acid, and so the pH was a little higher than 5. Actually, it was 5.07. So you can easily get the ratio of your weak acid to weak base to be at 5. All right, so again, it's going to resist changes in pH. You're going to, if you wanted a acid that, if you wanted a buffer that had a pH of 10, now you're looking for a pKa of 1 times 10 to the minus 10. All right, actually, you're looking for a pKb of 1 times 10 to the minus 4. All right, so if your pKa, If you're looking for a Ka, that is 1 times 10 to the minus 10, which would be a pKa of 10. Or, of course, a pKb of 4. So just like we had pH and pOH, your pKa plus your pKb is equal to 14. All right, and that just comes from the Ka times the Kb is equal to Kw. So you just take the negative log of both sides, and so that gives you that the pKa plus the pKb is equal to the negative pKw, but that is a constant of 1 times 10 to the minus 14, which gives you a number for that answer for 14. Again, they have to be conjugates. So you have to have a weak acid and its conjugate base. You have to have the weak acid and its conjugate base. They both have to be weak. They both have to be non-zero. You cannot have any H plus. You cannot have any OH minus. All right, and so you can buffer at any pH. When you have a certain pH you're looking for, you're going to have to go to a table of Kas and pick where the pH and the pKa are the most similar, and that would be the buffer to use to buffer at that pH. So if you wanted a buffer at pH of 5, then acetic acid would be great. If you wanted a pH of 10, acetic acid would be terrible. You would never get acetic acid to buffer at pH 10. You would have to pick a different acid-base system that has a pKa that is close to 10. And there is a capacity for your buffer. If you add too much H plus or too much OH minus, you would get a sharp change in your pH. But in the middle here, we have a buffer. When you add H plus, it reacts with the weak base, the A minus. So this reaction going this way, you have your H plus reacting with your A minus, and that's going to give you HA. So it's taking your strong acid and making it into a weak acid. That's what your buffer does. When you're adding OH minus, well, a buffer has A minus and HA. You add your strong base, your HA in this buffer is going to react with your OH minus to form H2O and your A minus. So it's making neutral water. And of course, it's making a weak base. So you add a strong base, it makes it into a weak base. You add a strong acid, it makes it into a weak acid. So when you add acid, the pH will come down, but it's going to come down slightly. Again, with the adding the strong base. You add the strong base, the pH is going to go up, but only slightly because it's going to make a weak base. If you add more OH minus, then you have HA. If you add way too much OH minus, then now there's no more HA to react with, and now you just have OH minus in there, and the pH is going to shoot way up. And that's what they're showing on the graph over here. You've used up all of your HA to neutralize that strong base. The pH is going to go straight up. Same thing on the other side. If you add too much H plus, now there's no more A minus to react with it. The pH goes down quickly. All right, so there is a buffer capacity. You can add too much H plus, you can add too much OH minus, and then no longer have a buffer. All right, so the two important characteristics is pH. Again, you're going to pick a buffer system that will give you the pH that you want. So some systems work great at a pH 5. You would pick acetic acid. Some work great at pH 10. You would not pick acetic acid. You would pick probably an ammonium with ammonia for that high of a pH. But you would get a chart of pH of pKa's or Ka's and Kb's. You convert those to your pKa's, and you have to pick the pH and the pKa that are the most similar to buffer at that pH. And again, buffer capacity, buffers work great, but if you add too much H plus or too much OH minus, you can then lose your capacity of the buffer. All right, so buffer questions are very tedious because you are mixing things together. And as soon as you mix something together, just like we did in the lab, we had the 5, the 5, the 5, and the 3. We had to do MV is equal to MV, get our new concentrations. That's what you're going to have to do with a lot of these buffer questions, including this one. So we are making up an ammonia buffer, right? So we have ammonium and ammonia. The buffer says to mix 60 mils of 0.1 molar NH3 with 40 mils of 0.1 molar NH4Cl. All right. So down here, they have written the KB reaction. All right. They did not have to write the KB reaction. They could have written the Ka reaction. The reason why they wrote the KB reaction here is because you can find the KB for NH3. The reason why they did not write the NH4 plus goes to H plus and NH3 is because that when you look up the Ka table, there is no Ka for NH4 plus. But again, if you prefer to do the Ka reaction, you know that that is the Kw divided by the Kb. All right, so once you have this Kb, you just take your Kw divided by Kb and you have the Ka. You can use either one. When you have both the weak acid and the weak base, either one of these reactions will give you the same exact answer for the pH. All right, so the problem here is we have to do MV is equal to MV. All right, this is a dilution. When you're doing a dilution, MV is equal to MV. That is always for a dilution. For our NH4 plus, we had a molarity of 0.1, a volume of 40 mils. 0.1, 40 mils. I want to know what the molarity is now that I am at 100 mils because I added the 40 and the 60 together. The NH3, I started with 0.10 molar with a volume of 60 mils. What is molarity now that my volume mixed together is 100? So I multiply by 0.1, that gives me 4 divided by 100. And so that is 0.040 molar for the NH4 plus. 0.1, that's 6, divided by 100, I have 0.060 molar for my NH3. All right, so now you have your initial concentrations. All right, and again, you can use the Ka, you can use the Kb. Doesn't make any difference. The Kb is 1.8 times 10 to the minus 5. All right, so let's use the Kb reaction here, and we have 0.06. Water is a liquid. We don't care about water. It is not in our equilibrium. NH4 plus concentration is 0.040. And the amount of OH minus added in this is 0. All right, so we have a reactant and we have a product. We have one of each that are not 0. That means that we do not have to do our Cb over our Kb. We know that our X1 value is our answer. We can't have a 0. We know it's going to the right. All right, so minus X, plus X, plus X. All right, we're going to neglect the minus X, the plus X. All right, and so at equilibrium, we're going to have 0.060. I'm not even going to write the minus X because I know it's so small. We have a non-zero concentration on both sides. We have a 0.040 and we have an X. All right, so we have our setup. We have our 0.040 times X divided by 0.060. And that is equal to 1.8 times 10 to the minus 5. All right, so that is 1.5 more than that. So I want to say it's 2.7, but I'm going to push the button. So 1.8 times 10 to the negative 5 times 0.06 divided by 0.04. Yeah, 2.7 times 10 to the minus 5. Should have went with my. All right, so I now have my X value. That is 2.7 times 10 to the minus 5. All right, and so here is where, if you assume that every time you get H, it's H plus, then you get the answer right half the time. This will be one of the times that you got it wrong, because when you use the KB and the OH minus started at 0, your X value is your concentration of OH minus. So you take the negative log of that, and that gives you your POH, which is a 4.57. And we know that the pH plus the POH equals 14, so we have a 9.43. So the pH of this is 9.43. Because pH plus POH is 14. All right, so whenever you're making a buffer, you're usually mixing some volume with another volume. You have to get a new concentration, and then you have to solve for your pH. At least you know when you have a reactant and a product, you never have to check your X value. You can, if you like, and take your 0.060 and subtract 2.7 times 10 to the minus 5, and you get 0.060. It does not change. You have 3 decimals minus 6 decimals. You give your answer to 3 decimals, and it doesn't change the value. All right, so that rarely, so rare that we say it's never going to affect any of the problems that we're going to do. We only get the first X value, and that is our final answer for X. All right, so notice that we had a buffer that had a pH that was high and a buffer that had a pH that was low. So let's go back to our acetic acid. So with acetic acid, we had a Ka value of 1.7 times 10 to the minus 5. And when we do the Kb, remember that the Kw divided by the Ka is equal to the Kb. And you can actually get a number, but anyway, what you need to know is when you take 10 to the minus 14 divided by 10 to the minus 5, you're going to get a 10 to the minus 10. So you don't need to know it's 10 to the minus, but you need to know that it's smaller than 10 to the minus 5. And so here we had the Ka was greater than the Kb. And that's why we had an acidic pH. And so the pH for that, we solved it, was 5.07. But if we had just the buffer, the perfect buffer, it would have been a perfect buffer at 4.77 as the pH. So if we had equal amounts of our acid and our base, 4.77 would have been our pH. Then we did the NH3. NH3 with the NH4 plus. All right, so this was our acetic acid. This was the second one, and then that one gave us a Kb. And so the Kb was greater than the Ka because the Kb was very close to that answer up there. It was 1.7 times 10 to the minus 5, and so your Ka is something times 10 to the minus 10 when you can solve for it exactly. But what you need to know is that your Kb is larger than your Ka, and so this is going to give a pH greater than 7. And that would be a good buffer. Oh, that was 1.8. 1.8? I think so. There. Kb was 1.8 times 10 to the minus 5. So if we take negative log of 1.8 times 10 to the minus 5, that gives us a POH of 4.74. And so this would be a great buffer at a pH of 9.26. So if you're looking for a buffer at 9.26, then an ammonium buffer would be a great choice. And so this one had a pH a little higher than that. And if we go back, why was the pH higher than 9.43? Well, because when we got finished with our MV is equal to MV, we see that we had a higher concentration of the weak base All right, it was higher than our concentration of our weak acid. If we had equal amounts, then it would have been 9.26. Since we had more of the base than the acid, it's slightly above the 9.26, and that is the 9.43. All right, so here comes the hardest, well, or the second hardest, I don't know. Yeah, probably the second hardest problem you're going to find is when you have a problem where you took 75 mils of this buffer solution. All right, so we had our 0.1 molar acetic acid, and we had our 0.2 molar sodium acetate. All right, we take 75 mils of this buffer. To that, we're going to add 9.5 mils of HCl. All right, so now we have three things, and we're mixing three things together. And so we have our HA, that we're going to do MV is equal to MV. We're going to have our A minus, which is going to have an MV is equal to MV. We're going to have an H plus. That's going to be an MV is equal to MV. So we have mixed these things together. We're going to have a new concentration. All right. And since we have added a strong acid, HCl, then you have no choice. You have to pick the, again, you have three choices. You got your Ka, you got your Kb, and you got your Kw. So you have to pick the one that has HA, A minus, and H plus in it. So you have to realize that that is the Ka reaction. No other reaction of the three has all of those three in it. And so the reaction that we're going to use is HA goes to H plus and A minus, and we know that Ka, it's 1.7 times 10 to the minus 5. We're doing acetic acid again. All right, but when we put in our initial, we have to do it always after mixing. And so we mix them together. So the molarity of my HA was 0.1 when the volume was 75 mils of that. What is my molarity now that we are 84.5 mils? Because we added the 9.5 mils of the HCl. A minus was 0.2 molar at a volume of 75. What is the molarity now that we are at 84.5 mils? And then your H plus. The H plus was 0.1 molar at a volume of 9.5 mils. What is the molarity now that the volume is 84.5? So we have a new molarity for all of these. So we have HA, that is a 0.089. So my HA is 0.089 molar. A minus is a 0.178. I'm going with 3 decimals for all the numbers. All right, H plus that is a 0.011. And I went with the same number of decimals because I know what I'm going to do next. All right. So if you have no zeros, then you have to go until something on the right is 0. Why is it something on the right have to be 0? Because on the right, H plus is a strong acid. And acid-base reactions always favor the weaker acid and weaker base. So this reaction highly favors the reactants, and we know that by looking at every Ka. It is the concentration of your products divided by your concentration of reactants, which means we have very few products and lots of reactants. It favors the reactant side. And so we are going to go to the left until something on the right is 0. So something on the right, maybe both things, but something on the right has to be 0. So I'm going to call this my new initial. All right, so you have your initial, but something on the right's not 0. So you're going to have a new initial. Something on the right, or both things on the right, have to be 0. And so it's going to shift until something is 0. And of course, the smaller concentration is the one that's going to go to 0. And so we lose 0.011. We lose 0.011. That makes the H plus go to 0. The key here is that most people forget that when you lose it on the right, you gain it on the left. And so you have to add 0.011. Most common error on this one for someone that's doing it pretty much right is to not add the 0.011, and then your answer is off slightly, but it is off. All right, so your new initial is 0.1 for your HA, 0 for the H plus, and 0.167 for your A minus. All right, so now we have a reactant, we have a product. We know that when we go to the right, we have to go to the right. You cannot have a 0. So now we know when you go to the right and we do a minus X, a plus X, and a plus X, since we have a reactant that is not 0, we have a product that is not 0, the minus X and the plus X does not change those numbers. And so we have, for our equilibrium setup, we have X, which in this case is H plus, times the 0.167 divided by the 0.1 is equal to the Ka, which is 1.7 times 10 to the minus 5. And when you push the buttons, you get an X value of 1.0 times 10 to the minus 5. So that is equal to X. X is equal to your H plus concentration. And so you take the negative log of that and you have the pH. Well, I can do the negative log of that in my head. That is a perfect 5, 5.00. All right, so when we did the original problem, first thing that we started with, we had 0.1 molar of acetic acid. We had 0.2 molar of sodium acetate. Our answer for that was a pH of 5.07. So that was our first answer when we just had the 0.1 molar acetic acid, 0.2 molar sodium acetate. Now we added HCl. So we know that the pH is going to go down. And as long as it doesn't use up all of the buffer, it's only going to go down slightly. And so how do you know if you used up all your buffer? Well, when you do the reaction has to go to the left until something is 0, if that something is 0 is your A minus, now you've lost your buffer. You don't have a buffer if this goes to 0. All right, but in this case, that one did not go to 0. It was the H plus that went to 0. And so you see that you still have your A minus concentration, you still have your HA concentration, and all of your H plus, all of your OH minus, everything else is 0. You have still a buffer. And so we added a pH 1 buffer to a pH 5 solution, and it only came down by 0.07. And that's what a buffer does. It gives you a very small change in your pH. It will change, but it will change very, very slightly. They do things anyway, a little bit different. They get, their sig figs are different than mine. They get a 4.96. Fine. All right, so if you like the way they do it, that's fine too. All right, so since we know, because we've said it 3 or 4 or 5 or 10 times, that when you have an HA and an A minus concentration, you don't have to worry about the minus X, the plus X. The first X value is the answer. We neglect those X's, and that's our answer. All right, so here's the Henderson-Hasselbalch equation. So you simply take your HA and you get your H plus and your A minus. I'm just taking the Ka reaction. And then you write your setup. So the Ka is equal to your concentration of H plus, concentration of A minus over the concentration of HA. We've done that a million times. All right, so Henderson-Hasselbalch just says, well, just take the negative log of both sides. All right, so we're going to take the negative log of both sides. Negative log of this side, negative log of that side. All right, so the negative log of the Ka, well, that's the pKa. The negative log of H plus, well, that's the pH. And we still have the negative log of your A minus over HA. All right, and then we solve for pH. So Henderson-Hasselbalch solves for pH. So we add the log of A minus over HA to both sides, and you have your final answer, which is the pH is equal to the pKa plus the log of A minus over HA. All right, now, since we have a buffer, that means you do have an A minus concentration, you do have an HA concentration. You're going to say, but we're putting in the initial concentrations for A minus and HA. Remember, your X values never change the initial concentrations when you have a reactant and a product. And this is a buffer, a reactant and a product. And so the X value never changes. So for every time you have an initial A minus and HA, that is also the equilibrium concentration of A minus and HA. All right, but the pH number, the H plus, is a 0. In order to have a buffer, your H plus has to be 0. So this is just a much quicker way to get the answer. If you recognize that you have a buffer, you simply plug in the numbers. So if I started with HA was the 0.10 molar and our A minus was a 0.20 molar, and the Ka was 1.7 times 10 to the minus 5, and you say that's a buffer, you throw it into the equation and your number, the answer just pops right out, and it's very simple. You can do it the long way if you want, but you solve for the pK. So pKa is the negative log of the Ka. So they give you the Ka, so it is the negative log of 1.7 times 10 to the minus 5, which is a 4.77. So that's your pKa. All right, and so your pH is equal to the 4.77, the pKa, plus the log of A minus, which was 0.2, over HA, which is 0.1. Make sure you have parentheses around that. You do the division first, then the log of that division. Make sure you're using your calculator correctly. And you push the buttons and you get 5.07. All right, so it's as simple as that. The first one we went through, it goes to the right, we wrote a reaction, all that stuff. If you recognize it to be a buffer, you go right into the Henderson-Hasselbalch equation. Again, people will say that's the initial concentration of your HA of 0.1 and your A minus of 0.2. Again, when you have a reactant and a product, the X values never change the numbers. Those are also the equilibrium numbers. All right, so that is the Henderson-Hasselbalch equation. It can be used anytime you have a buffer. All right, the hardest problems are going to be acid-base titrations because they will do every single problem that we have done in one question. All right, so an acid-base titration. All right, just like we did in lab. In lab, what did we do first? Well, we took our HCl and we added NaOH and we titrated it until it turned to light pink. All right, so when you do a titration, people will want to write the reaction this way. H2O plus NaCl. But I told you there's only 3 reactions that we're going to do. And the 3 reactions are the Ka reaction, the Kb reaction, or the Kw. When I look at that, I know for sure that's the Kw, but it's the reverse of the Kw. Because if you do the net ionic, you have a strong acid, so that's H plus and Cl minus. You have a sodium, all sodiums are soluble, NaOH, strong base, whichever way you want to know it. All sodiums are soluble, break up into ions 100%. Water's a liquid, always stays together. All sodiums are soluble, Na plus and Cl minus. And so you see that your spectator ions are the sodium and the chloride ions. All right, and so you end up with simply H plus OH minus yields water. So when you have a strong acid with a strong base, you only get water. And so the pH of this is 7. All right, but again, you could say that's not one of those three reactions. Well, actually it is. It is the reverse of Kw. All right, and so the way I would write it is as a Kw, H2O in equilibrium, that's a liquid equilibrium with H plus and OH minus, and I know that my Kw is 1 times 10 to the minus 14. Very, very small number. I know that it is going to go completely to the left. All right, so as long as you write these three reactions, then you know for sure that something on this left side, either the H plus or the OH minus, have to be 0. At the equivalence point, they are both 0. All right, and so it goes completely to the left until they're both 0, but you can't have a 0 because it is equilibrium, and so it has to come back as x and x, and so you end up with x squared is equal to your Kw, which is 1 times 10 to the minus 14. So your x value is 1.0 times 10 to the minus 7. And this one you can't get wrong, because if you said it was H plus, you're right. If you said it was OH minus, you're right. It's both. It is the H plus concentration, and it's also the OH minus concentration. So if you wanted the pH of pure water, you already know the answer to that. The negative log of 1.0 times 10 to the minus 7 is that, 7. If you wanted to know the pOH, you know that your pH and your pOH equals 14. So, of course, that's also 7. It's also the negative log of the OH minus concentration. And so they're both 7. But the only time that your equivalence point, pH, is 7 is when you have a strong acid and a strong base. All right, now the titration equation is completely different than the dilution. You may look at it the same, and in this case, you could say it is the same. You can never convince me it is never the same. All right, so MV over C is equal to MV over C. The reason this is not a dilution, this is a titration, where C is the coefficient of your acid. For the first one, I usually start with acid, doesn't matter. It's going to give you the same math answer. Base is the second one. And so that's the molarity of my acid. That's the volume of my acid. This is the coefficient of my acid. For the base, it is the molarity of the base. It is the volume of the base. It is the coefficient of the base. It is not the total volume. It is not, and it's the volume of just the base. On the left, it is volume of just the acid. It is not a dilution question. It is a titration answer. So at the equivalence point, you have molarity volume over C for your acid is equal to the molarity volume and your coefficient of your base. So you have to have a balanced chemical reaction. Realize in this one, they're both 1s, and it's going to look the same as a dilution. It is not the same as a dilution. A dilution is you're adding some other solution and we're getting a new molarity. That is not what this is doing. This is finding the volume that it takes to get to the equivalence point. All right, so when you do a titration, many times you will have a pH probe, and you'll add a certain amount of base, and the pH is going to go up. You write it down, and you do that for a lot of data points, and you're going to draw a plot. So you use a graph paper and draw a plot. We did not do that for our lab, but if we were to do that for our lab, you would have your pH on the y-axis, and you would have your volume of your base on the x-axis. And so, of course, we started by adding HCl, and so our pH was low. And then we added base, and so the pH started going up, and then we reached the equivalence point. And so this is what a titration curve would look like. And this would be your equivalence point, basically the center of that inflection point. That's going to be your volume at the equivalence point. This is your pH at the equivalence point. If we're doing the first titration with the H plus, HCl, and the OH minus, the pH number we know would be 7. But it is only 7 when you have a strong acid plus a strong base. The second reaction that we did was still the strong base, but we used KHP. So we had a weak base, a weak acid. So we had a weak acid, HA, and we added a strong base, OH minus. And again, when you do a titration, you want to do it the way that you're doing it in the lab, but it's not one of the actual reactions that you have to know. It's the reverse of that reaction. And so I realized that when you're adding stuff, you want that to be on the reactant side, but you should know that this, since it has OH minus, is going to be the KB reaction. And so you should be writing A minus plus H2O goes to HA plus OH minus. So this is your KHP, that's your weak acid, and this is your NaOH, your strong base. And now you have a KB reaction. All right, and so again, when you do a titration at the equivalence point, just like we did with our acid to base, strong acid, strong base, at the equivalence point, what that means is this number and this number are exactly the same number. So if this is 0.1, then this is 0.1. At the equivalence point, that's what that means. Those two are exactly the same, and they both will go to 0. People will see it as reactants, and then it goes to 0 to the right, and that's fine. I stick with my 3 reactions, and in this case, I'm going to start with things. All right, so here's my initial, which is odd because the initial here is 0 for the reactants, but things on the product side. But I know that I'm going to have a new initial. My new initial, something on the right has to be 0, or both things. The only time both things on the right are 0 when you're at the equivalence point. And so this is going to give you a 0.1 molar of your A minus. And so you see that when you're at the equivalence point of a weak acid and a strong base, you end up making a weak base. And so what you can tell me is that the pH is going to be greater than 7 at the equivalence point. The only time your pH is equal to 7 at the equivalence point is when it's a strong acid and a strong base, because that just makes water. When you have a weak acid and a strong base, that makes a weak base, which means your pH is going to be greater than 7. All right, and then of course the other example is going to be if I added a strong acid to a weak base. So if I added a strong acid to a weak base, all right, if I'm at the equivalence point, that means that this number has to be exactly the same as this number. All right, and so we see that that is going to make HA. All right, so again, when you're doing a titration at the end point, you start with something that the reactant is 0, and you have your two products. If it's at the equivalence point, they're going to be equal. They both will go to 0. And then you'll have to go to the right and see, get the Ka and all that to get your pH. All right, so, but again, here, if you have the equivalence point of a strong acid with a weak base, these are the only 3 we're going to do. We're going to do strong acid, strong base. We're going to do weak acid with a strong base. We are going to do a strong acid with a weak base. Those are the only 3 titrations. We will not be doing any weak acid, weak base titration. All right, when you have your strong acid with a weak base, you're going to form a weak acid. And so the pH is less than 7. All right, so again, the only time that your pH is equal to 7 is when it's a strong acid with a strong base. All right, equivalence point. Again, that is when you have equal moles, given the coefficients, that then they both will go to 0. You have equal amounts of your reactants. Of course, again, in the way I do it, it's going to be a Ka, a Kb, or a Kw, and they're going to be products. You can do it any way you want. This is the way I have decided to do it. Otherwise, you got to rewrite reactions in the reverse direction and all kinds of stuff. I just always have one of these 3, and I can do the whole problem with one of those 3 reactions. All right, so we use phenolphthalein. And phenolphthalein was an excellent choice of a indicator because it turns pink right above 7. So it's about 8, I think it's usually about 8.2. When you have a light pink, your pH is about 8.2. All right, so that is perfect for the second one when we had our weak acid with our strong base because the pH at the equivalence point was slightly above 7. All right, and so that was a perfect indicator for that. The first one, where it's a strong acid, strong base, not as perfect, but the equivalence point is right here at 7 for the strong acid, strong base. So you have to go slightly beyond it for it to turn pink. But again, if you look at how much to the right that is when it turns pink, it is a very, very small amount. You're talking a couple of drops. And so if you're off by a couple of drops, you are good for the titration. All right. So basically, now they're going to talk about limiting reagent and all this stuff. But the key is, if you do it this way, you don't have to worry about any of that nomenclature. What you always do is you write one of the three reactions. You write the Ka, you write the Kb, or you write the Kw. When you have both NaOH, a strong base, and HCl, a strong acid, that is when you write the Kw reaction. So you have water goes to H plus and OH minus, and we actually know the number for the Kw, the Ka, Kb, we have to look up the numbers. Kw, it is a constant, and it is 1.0 times 10 to the minus 14 that we use all the time, and so you would probably know that without looking at the constants table. All right, and so again, you're going to have to do MV is equal to MV. We are mixing 10 mils of 0.1 NaOH with 25 mils of 0.1 HCl. So we're not at the equivalence point. The equivalence point would be 25 mils and 25 mils or 10 mils and 10 mils. We are only adding 10 mils of 0.1 molar NaOH to 25 mils of 0.1 molar HCl. So we know that we're not at the equivalence point, so the pH is not 7. And we also know that we have more acid still in there than we had base added. So it's going to be a pH less than 7. All right, and so to find our new concentrations, we have to do MV is equal to MV for both the H plus and the OH minus. You will do a lot of MV is equal to MV. For the H plus, we have a molarity of 0.1 and a volume of 25. We want to know what is our concentration now that our volume is 35, because we added 10 to 25. For our OH minus, we had a molarity of 0.1, a volume of 10 mils. What is the new molarity now that the volume is 35 mils? Note when you have, molarity is always molarity, but volume can be any units. It just has to be the same on both sides. All right, and so I just stick with the milliliters. If you want to convert it to liters on both sides, you will get exactly the same answer. So you take your 0.1 times your 25, divide by 35. For your H plus, you have 0.0714. All right, and then you take your 0.1 times 10, which is 1, and divide that by 35, and you get 0.0286. All right, for every one of these, the Ka, the Kb, the Kw, something on the right has to be 0. All right, so you have your initial. When you look at your initial and nothing on the right is 0, you have to come up with a new initial. Something on the right has to be 0. And so that's why they're talking limiting reagents. So the one that is the smaller amount is the one that's going to go to 0. You can't subtract 0.07 from 0.02. That would give you a negative concentration. There's no such thing as a negative amount of something. All right, so we can subtract 0.0286. We can subtract 0.0286. And here's where you would add 0.0286, except it doesn't matter because it's a liquid. All right, so we don't care about that because that is not part of our equilibrium, but that is happening. We are making that much water. All right, and so our OH minus concentration is 0. Our H plus concentration, 0.074, is 0.0428. All right, and so you can't have a 0. It's going to go to the right, but look at this K value. 1 times 10 to the minus 14. So when you add your plus X here, there is no way that a K value of 10 to the minus 14 is going to change that at all. So you can do it, and you can see that it doesn't change it. You do not have to. This is your concentration of H plus. And so you go right to the pH, is the negative log of the 0.0428. The negative log of that answer is a 1.37. So the pH here is 1.37. All right. Now, if you wanted the OH minus concentration, you could do it one of two ways. You could do it by your pOH, which is a 12.63. And so it's 10 to the negative 12.63. Or you know that your H plus concentration times your OH minus concentration always equals Kw. We know our H plus concentration is 0.0428. And you just solve for OH minus. Divide both sides by the 0.0428. So you take 1 times 10 to the minus 14, and you divide that by 0.0428. And that gives you a 2.3 times 10 to the minus 13. That is your OH minus concentration. So you can do that. 10 to the minus 12.63 is 2.3 times 10 to the minus 13. So that's how you get your concentration of OH minus. Again, nothing is 0. It's so small it will have no effect on anything, but it is not 0. It is in equilibrium. We do not have zeros. All right, so yeah, so this one, that pH is, so this one is showing that your equivalence point is above 7. So this is the titration of your weak acid with your strong base, because when you take your weak acid with your strong base, you get water, but you also get A minus. So that is a weak base. That means that your endpoint will be above 7, and that is when it is a perfect indicator to use phenolphthalein. When you do the strong acid with the weak base, you don't want to use phenolphthalein. Then you've got to use a different one, and that would be the brome cresol green, which changes colors down at a pH below 7. When we do that, you'll see how much more difficult it is to see a color change from one color to another color versus no color to a color. No color to a color is very easy to detect. All right, so now we want to calculate the pH of a solution at the equivalence point. These are, I think, the hardest question, because you have to calculate what is the volume. You have to do MV is equal to MV, and then you can answer your question. And the equivalent point is not a buffer. The equivalence point is when both things on the right are 0 after your new initial. All right, so I have to see what I'm doing here. I have a pH of a solution at the equivalence point. I have 25 mils of this acid. It is not one of the 6 strong acids. This is a weak acid. I call it HA. It is titrated with sodium hydroxide. All sodiums are soluble. I write this as my OH minus. And so I need to have a reaction that has HA in it and OH minus in it. And I know that the only reaction that has both HA and OH minus in it is my KB. But they didn't give me a KB, they gave me a Ka. Well, that's all right, because I know that Ka times Kb is equal to Kw. So I simply take my KW, divide by the KA that is given to me in the problem, and then I have my KB constant. All right, and so I write the KB. Again, A minus plus H2O goes to HA plus OH minus. Anytime you're doing a titration, you're adding products in the way that I do it. It's the way I will always do it. Initial, when I'm doing a titration, that's 0. I'm adding my HA, all right, except I don't know what my volume is. All right, I do know that I am adding 0.1 molar NaOH, so I know I'm going to have to do MV is equal to MV, but before I can do MV is equal to MV, I have to solve for the volume at the equivalence point. And so before I do MV is equal to MV, I have to do the titration. And the titration is acid MV over C is equal to base MV over C. All right, and so I have my acid numbers. I have a molarity of 0.1. I have a volume of 25. I have a coefficient of 1 for my base. My base also has a 0.1 molar. The volume is what I'm solving for, and the coefficient again is 1. All right, so you don't need a calculator to figure that out. It's 25. All right, so the volume at the equivalence point, volume of NaOH at equivalence point is 25. All right, so now we know that we're doing a dilution. MV is equal to MV is a dilution. And so my HA was 0.1 molar at a volume of 25. Now that we're at the equivalence point and we added the 25 mils of our NaOH to get to the equivalence point, now my volume is 50. And so the molarity is 0.050 molar. It would be exactly the same numbers for the NaOH. They happen to start at the same concentration, 0.10. All right, and by our calculation, we know that it took 25 mils of that to reach the endpoint. All right, what's the molarity now that we're at the equivalence point where we have the 25 mils of both the acid and the base? And so our total is 50 milliliters. And so again, 0.050. All right, and you don't actually have to calculate both of them. If you know for sure you calculated one right, the other one is the same because of the question. The question says at the equivalence point. And what that means is the concentration of your HA is exactly the same as your concentration of your OH minus. All right, so my initial concentration of A minus is 0, HA 0.05, and 0.05. My new initial, one of these is going to go to 0. But at the equivalence point, actually, both of these go to 0. That's 0, that's 0. And so this is your 0.050. So you subtract the smaller number. Well, the numbers are the same. At the equivalence point, that is a requirement. That's what the equivalence point means. They are both exactly the same. They both go to 0. All right, but you can't have a 0. That's why it's called a new initial. We have to reach an equilibrium. The 0 is not absolute 0. It's a small number, but it is not 0. Now we don't have something on the other side. Now we have to use our concentration of base divided by Kw to see if that's over 1,000. So our concentration of our base over Kw, okay, Kb, that has to be greater than 1,000. All right, again, we had to use Kw divided by Ka in order to get our Kb. So our initial concentration, our new initial concentration, 0.05, the Kb. So to get the Kb, we have to take the Kw, 1 times 10 to the minus 14, divide by the Ka, 1.4 times 10 to the minus 5, and that gives us a 7.1 times 10 to the minus 10. All right, and that is going to be way greater than 1,000. So we know that we can neglect the minus x. So minus x, 0.050 minus x is going to be 0.050. The CB over KW is much greater than 1,000. All right, and so this is X and this is X. And so we have, X squared over 0.050 minus X, but we just said we can neglect X and we don't have to check it. And that's equal to KW. KB. Make sure you are looking at the reaction. You know this is a KB reaction, so you must use the KB constant. Don't do all this work and use Ka and get the wrong answer. All right, and so you have to use KB, which we calculated as 7.1 times 10 to the minus 10. So 7.1 times 10 to the minus 10 times 0.05, and then the square root of that gives us a 6.0 times 10 to the minus 6. All right, so again, if you say X is always H plus, well, you got it wrong this time as well. You got to look and see what X is. X is your concentration of OH minus, and so that is your OH concentration. And so you're going to get your POH. So the negative log of that is your POH, which is 5.22. So your POH, 5.22, and then your pH is 8.78. All right, so, and when you look at this problem, we're at the equivalence point. So we're at the equivalence point of a strong base with a weak acid. We are making a weak base. So that question comes out to be, what is the pH of a 0.050 molar weak base? So we know that pH is going to be greater than 7. All right, and so here is your titration curve. So this time you have in your Erlenmeyer flask, when you're doing this titration, you have, well, it's not an Erlenmeyer flask, all right. Erlenmeyer flask, this is going to be your weak base. And then you're going to drip in your volume of HCl. All right, so this one is going to have your HCl here. This is going to be your A minus, your weak base here. All right, so when you throw in your pH probe goes in your Erlenmeyer flask, and so that's going to have a high pH because we have our base in it. We're going to be adding our HCl, and so the pH is going to come down. All right, and this is where you cannot use phenolphthalein. Phenolphthalein would have changed colors right in this area where it is, once it hits 8.2, it's going to go colorless, but your equivalence point isn't till you have a pH of the 5 point, whatever we got, 5.6, whatever. And so we have to pick you have many different choices for your indicators. Phenolphthalein works great for when you're adding a strong base. If this is a strong base, you're going to use phenolphthalein every time. But when it is a strong acid, you cannot use phenolphthalein. In this case, they use methyl red, you can use bromine cresol green. You have to have something that changes the pH in the acidic range when it's doing its color change. All right, so next time we're going to do a problem that is a titration from start to finish, which will be a very long problem.